NENOMATICA, where mathematics meets YouTube excellence. In this lesson, our problem is about money changing over 3 years, and we will solve for the initial amount. Here is our example. After each of the first 2 years, the student spends $100, then adds 1/3 of what remains. In the third year, the student spends $100 again. After these 3 years, the amount of money equals twice the original amount. We will find the initial amount and interpret the sign carefully. To keep everything organized, let us sketch a simple timeline of the 3 years. Each box is a year. Arrows show the operations we do. Subtract 100, then add 1/3 of the remainder, and so on. This will anchor the algebra we write next. Notice the leftmost box is the starting point, labeled x. In year 1, minus 100, then plus 1/3 of the remainder. In year 2, minus 100, then plus 1/3 again. In year 3, minus 100, and we are told the result equals twice x. Step 1. Define the variable. Let x be the initial amount of money. Step 2. After spending 100, the amount is x minus 100. Then add 1/3 of that remainder. So the new total is open parenthesis x minus 100 close parenthesis plus 1/3 times open parenthesis x minus 100 close parenthesis. This simplifies to 4x minus 400 all over 3. Step 3. In year 2, spend 100 again, then add 1/3 of that new remainder. First subtract 100 to get 4x minus 700 over 3. Then add 1/3 of that, yielding 16x minus 2,800 over 9. Step 4. In year 3, spend 100 once more. So the amount becomes 16x minus 3,700 over 9. We are told this final amount equals twice the initial amount. That is 2x. So we set 16x minus 3,700 over 9 equal to 2x. Step 5. Solve the linear equation. Multiply both sides by 9. We get 16x minus 3,700 equals 18x. Move terms to one side. Negative 2x equals 3,700. Finally divide by negative 2. So x equals negative 1,850. The negative sign means the student started in debt. Interpreting the context, the initial amount of money was negative $1,850, which corresponds to borrowing that amount. In this quick example, we will model a spring with a simple linear function and compute its length for a given mass. Let us visualize. On the left is the relaxed spring of 10 centimeters. On the right, we hang a mass of x kilograms. The spring stretches to a new length, which we call y. Experiments show a simple linear model fits. Y equals 0.8x plus 10, where x is in kilograms and y is in centimeters. Now we are asked for the length when x equals 5 kilograms. Substitute x equals 5. 0.8 times 5 is 4. Then y equals 4 plus 10, which is 14 centimeters. Example. We will solve a daily schedule fraction problem step by step. Hamid rests 1/3 of the day at night. He spends 6 hours at school. He dedicates 1/4 of the day to studying. He dedicates 1/8 of the day to pre-assigned tasks. The rest of the time is for sports. How many hours is that? To visualize 24 hours, we draw 24 equal boxes in a row. Each box is 1 hour. First, color the known parts. Rest is 1/3 of a day, which is 8 hours. School is 6 hours. Studying is 1/4 of the day, another 6 hours. Pre-assigned tasks are 1/8 of the day, which is 3 hours. The last box will be the sports time we do not yet know. Let x be the fraction of the day used for sports. The parts must add to 1 whole day. So 1/3 plus 6 hours out of 24 plus 1/4 plus 1/8 plus x equals 1. Now convert each fraction to 24ths. 1/3 is 8 over 24, 1/4 is 6 over 24, and 1/8 is 3 over 24. Add the numerators. 8 plus 6 plus 6 plus 3 equals 23. So 23 over 24 plus x equals 24 over 24. Subtract 23 over 24 from both sides. Therefore, x equals 1 over 24 of the day. 1 over 24 of a day is 1 hour. So the remaining box is the sports time, 1 hour. Final answer. Hamid spends 1 hour on sports each day. In this example, we'll solve a classic algebra problem about three consecutive odd integers, whose sum is 135. The sum of three consecutive odd integers is 135. Find the three numbers. Step 1. Represent three consecutive odd integers using a variable. We'll call the first number x. Then the next two odd numbers are x plus 2 and x plus 4. Step 2. Their sum is 135, so we write x plus the quantity x plus 2 plus the quantity x plus 4 equals 135. Step 3. Expand and combine like terms. X plus 2 plus x plus 4 equals 135. That simplifies to 3x plus 6 equals 135. Step 4. Subtract 6 from both sides to isolate the x term, giving 3x equals 129. Then divide both sides by 3 to get x equals 43. Step 5. The three consecutive odd integers are x, x plus 2, and x plus 4. Substituting x equals 43 gives 43, 45, and 47. As a quick check, their sum is 135. Final answer. The three integers are 43, 45, and 47. In this example, we will find three consecutive even numbers whose sum is 42. We'll set up a clean algebra model, solve for the variable, and then verify on a number line. Problem. The sum of three consecutive even numbers is 42. What are the numbers? To model consecutive even numbers, let the first be 2x. The next even number is 2 larger, 2x plus 2, and the third is 2x plus 4. Now write the sum equation. 2x plus 2 plus 2x plus 4 equals 42. Combine like terms. 2x plus 2x plus 2x is 6x. 2 plus 4 is 6. So we get 6x plus 6 equals 42. Subtract 6 from both sides to isolate the variable term. That gives 6x equals 36. Now divide both sides by 6. So x equals 6. Substitute x equals 6 back into the three expressions. 2 times 6 is 12, 2 times 6 plus 2 is 14, and 2 times 6 plus 4 is 16. Example. We will solve a classic savings problem and follow the exact step order shown on screen. Here is the problem. Saeed has $1,000 and saves $200 per day. Sarah has $1,200 and saves $150 per day. After how many days will their money be equal? To build intuition, let's sketch money versus days. The red line shows Saeed, 1,000 to start and plus 200 each day. The blue line shows Sarah, 1,200 to start and plus 150 each day. Where the lines cross, their totals match. Now we follow the exact algebraic steps. Step 1. Form the equality of totals. 200x plus 1,000 equals 150x plus 1,200. Step 2. Collect like terms by moving x terms to the left and constants to the right. 200x minus 150x equals 1,200 minus 1,000. Step 3. Simplify both sides. That gives 50x equals 200. Step 4. Use the division property of equality. Divide both sides by 50 to find x equals 4. Therefore, after 4 days, their money is equal. Example. We will solve a classic ages problem using algebra and a clear visual model. A father is 38 years old and his son is 8 years old. After how many years will the father's age be 3 times the son's age? Let's model the situation. We will show the father and the son now. Then we will add x years to both. That gives the equation. 38 plus x equals 3 times the quantity 8 plus x. We will now solve the equation. The equation is 38 plus x equals 3 times the quantity 8 plus x. First, distribute the 3. 3 times 8 is 24, and 3 times x is 3x. Next, move like terms to opposite sides. Subtract 24 from both sides, and subtract x from both sides. Simplify. 38 minus 24 is 14. 3x minus x is 2x. Finally, divide both sides by 2. We get x equals 7. Let's check the result. After 7 years, the father's age is 45, and the son's age is 15. And indeed, 45 equals 3 times 15. Initially, Sarah has 5 times as much as Fred. Now, we follow the algebraic steps precisely. If x is Fred's money, then Sarah's money is 5x. Next, incorporate the $100 transfer. If Sarah gives Fred $100, Sarah's money becomes open parenthesis 5x minus 100 close parenthesis, and Fred's becomes open parenthesis x plus 100 close parenthesis. The condition says Fred then has twice Sarah's money, so we write 5x minus 100 equals 2 times open parenthesis x plus 100 close parenthesis. We now simplify in the exact same order. First, expand the right side. 5x minus 100 equals 2x plus 200. Next, gather like terms. 5x minus 2x equals 200 plus 100. That gives 3x equals 300. Divide both sides by 3 to solve for x, giving x equals $100 for Fred. Finally, $100 for Fred. Finally, substitute x equals 100 into 5x. That yields $500 for Sarah. Therefore, the final answer is Fred has $100 and Sarah has $500. Fred has $100 and Sarah has $500. Example: the sum of 5 consecutive multiples of 3 is 75. Find all 5 numbers. We will follow a simple algebraic pattern exactly as written on screen. Before the algebra, here's a quick picture. Think of a middle value x and steps of 3 to the left and to the right. That makes 5 numbers x minus 6, x minus 3, x plus 3, and x plus 6. Step 1. Consider the 5 numbers in order x minus 6, x minus 3, x plus 3, and x plus 6. Step 2. Write their sum equal to 75. The constants minus 6, minus 3, plus 3, and plus 6 cancel out, leaving 5x equals 75. Step 4. Solve for x by dividing both sides by 5. That gives x equals 15. Step 5. Substitute x equals 15 back into each expression. In the same order, x minus 6, x minus 3, x plus 3, and x plus 6. Therefore, the 5 consecutive multiples of 3 are 9, 12, 15, 18, and 21. In this example, we add the same number to the numerator and to the denominator of a fraction. We want the new fraction to equal 3/5. Here is the starting fraction 7/15, and here is the target fraction 3/5. Think of each bar as a whole cut into equal pieces. We will not literally add pieces to the bar. Instead, we will set up an equation that adds x to the numbers 7 and 15, so the value matches 3/5. Set up the algebraic condition. After adding x to both the numerator and the denominator, the value becomes 3/5. To solve, clear the fractions by cross-multiplying. 5 times the quantity 7 plus x equals 3 times the quantity 15 plus x. Distribute to remove parentheses. 5 times 7 plus 5x equals 45 plus 3x. Move like terms to opposite sides to gather the x terms together and the constants together. Subtract 3x from both sides and subtract 35x from both sides and subtract 35 from both sides. Now simplify both sides. 2x equals 10. Finally, divide both sides by 2. X equals 5. Quick check. Adding 5 to both numbers gives 12 over 20. That reduces to 3 over 5. So our solution is consistent. In this example, we will solve exactly step by step, matching the structure shown. We start from the equation, open parenthesis 17 minus x close parenthesis, over 20 equals 3 over 5. Example. Step 1. Write the starting equation. Open parenthesis 17 minus x close parenthesis, over 20 equals 3 over 5. Step 2. Cross-multiply to eliminate denominators. 5 times open parenthesis 17 minus x close parenthesis equals 3 times 20. Step 3. Distribute 5 on the left and compute 3 times 20 on the right. That gives 85 minus 5x equals 60. Step 4. Move constants to isolate the x term. We write 5x equals 85 minus 60. Step 5. Simplify the right side. 5x equals 25. Final step. Divide both sides by 5 to solve for x. The solution is x equals 5. Example. From the number of biscuits Mary had, she gave half to her mother and half of the remainder to her brother. 5 biscuits remained for herself. Find the original number of biscuits. Let's visualize the situation first, then translate it into an equation. Translating the diagram to algebra gives the total on the left equals the sum of all parts on the right. Step 1, x equals 1/2 x plus 1/2 times 1/2 x plus 5. Step 2, simplify the product to 1/4 x. Combine like terms. Subtract 3/4 x from both sides. Rewrite the left as the common denominator expression. Simplify the numerator. Recognize 1/4 x equals 5. Finally, multiply both sides by 4 to find x. A quick sanity check. If x equals 20, then half, 10, go to the mother. Half of the remainder, 5, go to the brother. That leaves 5 biscuits for Mary. The arithmetic matches our story perfectly. Therefore, the original number of biscuits was 20. In this example, we will use a simple linear growth model to find how long it takes a salamander to reach a target length of 80 centimeters. A salamander lays between 30 and 70 eggs in spring. About 90 days later, the babies hatch. A newborn is about 30 centimeters long. During the early years, the length increases by 22.5 centimeters per year on average. How many years does it take to reach 80 centimeters? Let us visualize the growth. We place years on the horizontal axis and length in centimeters on the vertical axis. The line shows L equals 30 plus 22.5 times x, a straight line because the growth rate is constant. A 1-year step to the right raises the length by 22.5 centimeters. We model the length after x years using a linear equation. L equals 30 plus 22.5 times x. We want the time when the length becomes 80 centimeters. So set L equal to 80. Subtract 30 on both sides. Divide by 22.5 to isolate x. Now compute the value to get approximately 2.22 years. On the graph, the height 80 centimeters is a horizontal line. Where it intersects the growth line gives the required time. Draw the vertical drop to the time axis to read x. To build intuition, compare whole year marks. At 0 years, the length is 30. After 1 year, it is 30 plus 22.5, which is 52.5. After 2 years, it is 75. A little more than 1/5 of a year later, it reaches 80. Therefore, the salamander reaches a length of 80 centimeters after approximately 2.22 years. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.